Okay, so hopefully this is going to be about a 10-minute video where I'm going to explain how to do the key measurements to the Hubble's law lab. It's going to seem daunting at first, but it's really not so bad once you get the hang of it. I'll do my best to give you some background so you don't feel like you're making measurements and you have no idea what's going on. Basically, what you can do is upload your spreadsheet and graphs and then a few calculations with a conclusion. And I've spelled that all out here at the very end, okay? But let me go back a little bit. So here is a background. So the very first page is a copied PDF that gives you a background on Hubble's law. And so it's very important to read. There's two equations on there that are going to be critical for your spreadsheet. Okay, one of them is based on the Doppler effect. That's what I do in the lab now. So hopefully that looks fairly familiar. Then the rest are basically all the instructions, not only for what measurements to make and how to do them, but what to do in terms of analysis, calculations you have to do. So I think it's pretty clear what you have to do. You might have to read things a few times, but you can handle that. The other part I want to show you is the spreadsheet. Okay, so the spreadsheet that I put together looks pretty daunting. Okay, there's a lot there, but it's not too bad. We're going to look at maybe 10 or so galaxies. I've color coded them to differentiate between calculations, measurements, and givens. So if you scroll down, it's easy to miss because it doesn't come up right away. But anything that's a rose color is a measurement you're going to make using the website. Anything that's this tannish color is a calculations where you're going to have to type an equation. So I want you to continue learning how to do that. Remember, all equations in spreadsheet starts with an equal sign. And then once you type in a calculation, in this case for the redshift, that's the Doppler effect, you can use that square to fill down so you don't have to type it in every time. And lastly, the greens are givens. They're important constants for the lab. One is the standard size of a galaxy. In this case, it's 22 kiloparsecs, which is a funky distance unit. Kilo is 1,000. Parsec is, I don't know, a multiple number of light years. I don't remember how many. And then off to the right here, barely on there, let me scroll over, is the speed of light. Okay, so speed of light we want in kilometers per second because of astronomical units. And so I've already entered 300,000. All right, so let's go back to how to go do this lab. So if you go to the second page, there is a very important link that takes you to the actual galactic data. It's based out of the University of Washington in St. Louis, but it's actually based on data that was taken in the 1970s, I believe, from a telescope in Arizona. Okay, so the key thing we want to do here is this clickable galaxy images and spectra. So I click that, it's going to take us to the things we want to see. And you see a whole list of galaxies, so they're got a very nondescript name. NGC stands for New Galactic Catalog, and just whatever number. You don't have to go through all these. If you pay attention on the spreadsheet, I've listed the ones I want you to look at. Okay, so they are in numerical order, I believe, except maybe the last one. I added one, yeah, because I thought it was better than the one I had previously chosen. Okay, so you might have to skip around, just make sure you follow them carefully. All right, so image. We want to look at two sets of data. One is an image to help us figure out how far away the galaxy is, and the other one is their spectrum. In other words, what we see of the light coming from them to help us determine how fast they're moving. That's where the Doppler shift is coming, because we should expect the colors that we see to be shifted either to the bluer side of things or to the redder side of things. Okay, so let's start with the image. So I click on an image, you get a black and white, a negative, I should say, not a black and white, image of a distant galaxy. These things are stars within our own galaxy. The galaxy is usually centered on these photographs. Okay, and they're spiral galaxies. So one of the key assumptions of this lab is we're going to look at spiral galaxies as opposed to elliptical galaxies, which complicate things. Our Milky Way is a spiral galaxy, has this general shape. All right, so here is the idea. This photograph, this galaxy appears to be a certain size to our eye, or in this case the telescope. It has an angular size. That's what we're going to measure. We know, or one of the assumptions is that this galaxy's actual size in actual distance units, in this case kiloparsecs, is the same as our galaxy. It's not a perfect assumption, but it's close enough for our purposes. So if we can get the angular size, think of that as like theta, right? And we know the actual size, then we can use simple trigonometry, a simple ratio, SAR, from math, to get the distance of this galaxy. So how do we go about doing that? Well, the key thing is you got to locate where is exactly the galaxy. So since this is a negative, the brightest part is going to appear blackest. And then as it gets dimmer, it gets, more and more almost like a gray. It blends into the background. So if I look right about here, I can convince myself I still see an arm. So I'm going to say this is one edge of the galaxy. I'm going to follow along an axis. Think of the major axis of an ellipse. Okay, whoops. And I'm going to click to where I think the edge is. And here I'm kind of guessing. So if I click here, click once, I should see this come up. And it's telling me it measured a point, a pixel. And then I'm going to go here, and I'm going to go where it's as faint as it can be, and I say it's still a part of the galaxy. I'm guessing a little bit here. I'm trying to maybe use a little bit of symmetry, but not too much. And I click there, and it gives me the angular size in milliradians, all right? 10 to the negative 3 radians. So that's how tiny these things are to our eye. That's because they're so far away. Now, if I'm saying, well, I guess in that one, I'm going to try it again, I can just do try again. I'm going to click here, click there, and ooh, I got a smaller number. So how do I know which one's right? Well, I don't. So I might take an average of the two, or I might do it again. And what you want to be careful is you don't want to undermeasure. It's easy to undermeasure. There I get 1.064. Okay, so whatever I decide to choose, I go to the spreadsheet, and I go where it says angular size, and I enter in that value. So I use that value. Here is the actual size of the galaxy already given, and so eventually what you'll do is go over here where it says distance, and you'll plug in an equation based on angular size and actual size of distance, and get the distance in megaparsecs. So whereas the galactic size is kilo, which is thousands of parsecs, the actual distance is millions of parsecs. So we're talking tens or hundreds of millions of light years away, and those are considered nearby galaxies. All right, so that's the distance part, and again, that's all explained on the sheet. So let's go to the more interesting part, and probably the least, we understand the least. Okay, so if I want to go back to the list, I just click this image. All right, now I want to get the spectral data from this galaxy. I want to know how fast it's moving. And this is not going to look like anything you've seen before, so bear with me. So you're going to make 3 measurements, 3 independent measurements of the same, not the same thing, but it's going to give you the same calculation, so we can take an average. This is the spectral lines. So this graph here represents different color wavelengths. This is the x-axis, this is just relative intensity of light passing through the galaxy. And the reason these spikes show up is because certain elements are in that galaxy, and they absorb those colors, so they make a noticeable drop. This is called an absorption spectrum. And we know what elements are in a galaxy, and they're the same elements that we have here on Earth. So the key thing is all elements have a distinct fingerprint that identifies them. And we know what wavelength they should be absorbing particular light. And that's what these lines down here are. So for this case, these 2 lines are calcium. So we know there's calcium coming from those galaxies, and there's 2 lines of calcium, K and H. So in the lab, if we pass light through vaporized calcium, we should expect to see 2 distinct lines that correspond to this, and we can get their wavelength. So if I click on here, and I have to scroll down, I get that wavelength. And then if I want to click on the calcium H, what its wavelength is measured in a lab. In other words, not moving relative to us, I scroll down and I get a different wavelength. Now I'm going to tell you a little shortcut. You don't have to do that every time because it's going to be the same number for every calcium K and calcium H line. It is what it is, no matter where it is. All right, so that's the lab measurement. So if I go to the spreadsheet and I find calcium H and calcium K, there are 2 columns for each. One is lab wavelength, and then we got to get the observed wavelength. That's the Doppler shift. In other words, what wavelength does it appear to be coming from that galaxy because that galaxy is moving relative to us. So if I go back to that spectral lines, so here is where, because if the galaxy wasn't moving relative to us, we would expect to see a major dip right below us, right above that. And it looks like there is, but it isn't. And then I would expect to see the same thing for H. Where I see the major dips are right here and right here. In other words, they're shifted to the right. They are shifted towards the longer wavelength. So that's a redshift. Longer wavelength corresponds to lower frequency or redder. Okay, so I want to get what the measured wavelength is coming from that particular galaxy. So I click at the lowest point. And again, doesn't look like much happened, but if I scroll down, I get a wavelength in angstroms. Angstroms is a chem unit, means times 10 to the eighth, negative eighth, excuse me. And then I do the same thing for the H line. And I click that, and I get a different wavelength. And if I go to the spreadsheet, I would go to observed and observed. I have H and K here. I'm going to switch these to K and H so that they match up the left and the right. All right, there's a third one I can get to help me take an average, and that's over here. And this looks different because it's an emission spectrum. So rather than absorbing light, it's what it's emitting. The point is, this is for hydrogen, and there is a lab wavelength. You can just look if you scroll up, or you can click on it, scroll down. And then there is a shift. And a shift is going to come from the tallest, or I should say, you'll see two tall peaks for every spectrum. They won't all be always this noticeable, but you should see to the right two peaks, and you always take the wavelength for the left more peak. So I go to the peak, click it, and like before, scroll down. There is the shifted wavelength. I go to my spreadsheet, I add it under the pink, and then I have three sets of lab wavelengths and measured wavelengths. So what I'm going to do is for each one I'm going to calculate a Z. Z is the shift, the percent shift really. And again, that's in the lab notes. You'll do a calculation. You'll get three numbers. Ideally they're the same value, but they're probably not going to be. And then you do an average. Now if one of the numbers is radically different than the others, don't include that. But otherwise we usually want to use all three. So once you have the average Z shift, now you can relate that to the Doppler equation to the velocity. Okay, so again, that's pretty straightforward. And now we're going to have two sets of data. We have our x-axis for distance, our y-axis for velocity. You're going to plot them. You should get a line. It's not going to look pretty. There are going to be some outliers, but I give some instructions on how to try to do min and max. So we're going to try it a little bit differently, a little bit more crudely, but I think it can work. And then from the lines, you can find a slope. That slope is called Hubble's constant, one of the most important numbers in astronomy. We're still trying to fine-tune the value of Hubble's constant because its value tells us so much about the universe. And perhaps the most interesting thing, at least for this lab, is we can use it to find the age of the universe. So good luck. Ask me any questions you have through Schoology or email, and I hope you enjoy this.